All right, record to the cloud. All right, we are now recording. So hello, everybody, or everybody that was able to find the link. So I'm Josh. I am both the president of the PGSA and the one presenting this tutorial today, the machine learning workshop, as I call it. So I'm just extending the Zoom screen so I can see all of you guys. Okay. You guys can all see the PowerPoint? Perfect. Okay. So just to repeat what I was saying earlier, this workshop does come with some Python scripts and a data file. So there should be 6 Python scripts and 1 data file that we'll be using later on. If you're watching this on the YouTube channel, hi. And you can find these files in a link in the description below. Be sure to like, comment, and subscribe. All right. So first of all, what is machine learning? So machine learning, so by the way, I am not a machine learning scientist. I use machine learning in my research. So like my definitions for things may not be like the actual formal definition that an actual data scientist would tell you. But to me, machine learning is just the computer algorithms that find patterns in data. And these algorithms should become better as more data is presented, meaning that the algorithms can learn. So there are 2 main types of machine learning. There's supervised learning and unsupervised learning. So we'll start with supervised. In supervised learning, your data set has inputs and outputs. And the algorithm learns by comparing its predictions to the outputs. So you give it a list of the inputs and outputs, and it'll train itself by comparing the outputs that it predicts to the outputs that you gave it. And it'll try to adjust the model in order to make the predictions and the outputs the same. So here's a little diagram that describes that. You give it X, your inputs, it makes a prediction, and then I put it as the person saying, wrong, that's not right, it should be Y, and then it'll adjust. But this is all done in the computer itself. You probably know that already. And now for unsupervised learning. Unsupervised learning, data only contains inputs. So there's no like outputs. So the algorithm is going to then try to find patterns or clusters. So essentially you just, the stick man gives the computer a data set, and the computer will say, well, data points A and B are kind of similar. They belong in the same cluster. And then it'll give you back the clusters, and you can decide what those clusters represent. Those are the 2 main types of machine learning. And I lied. There's actually a 3rd type that's more modern. And that is called reinforcement learning. So reinforcement learning is kind of like the data itself gets generated during the training. So the AI itself is kind of making its own data. So this is typically used for game applications. So here's kind of a fun example of Pac-Man. So the controller of Pac-Man is the AI, is like a deep neural network or something. And it takes in its environment. So the environment could be like, the actual like game board. And it then uses that environment to, like it takes that environment into a neural network, and then the output of the neural network is an action. So, move left, move right, move up, move down. And using some sort of reward system, you can say like, it'll train itself in order to maximize that reward. Hopefully that makes sense. So yeah, as I said, this is usually used for video game AI, but it also, I've seen it used for designing like photonic systems. So like you want to maximize the intensity of light over here, and you have some nanoparticles that you want to form into a metasurface, right? So you can then like, the AI will train itself to like, well, here's what the intensity is over here. So now I'll move this particle up here to increase the intensity, and it'll actually design metasurfaces. That's one example in the field of photonics where I've seen this used. It's not efficient. This is not an efficient way of designing things, but it is a cool thing that if you do it right, you might get a paper out of it. So yeah, in this case, the computer is the captain now. So this is a really cool diagram that I found of machine learning. So it shows you your supervised, unsupervised, and reinforcement learning. And so for supervised learning, you typically have classification and regression. So classification refers to when your output are classes. So let's say your input is pictures of animals, and the classes can be dog, cat, cockatoo, whatever. And the goal of the classification algorithm, the goal of supervised learning in this case is to take that picture as an input and give it a label. You know, this is a dog, this is a cat. So that's what your phone does actually. When you take a picture on your phone, it actually gets run through a neural network and it tries to classify whatever the picture was. So that's why we go to your Photos app, you can type in dog and it'll actually give you all the pictures you have on your phone of a dog. Regression is more like a function. So regression, you have kind of continuous inputs and continuous outputs. So for example, regression, and an example of regression could be like you input the size of a house, the number of bedrooms it has, the number of bathrooms it has, and an output is going to be the cost of that house. So regression you can kind of think of as fancy curve fitting. And unsupervised learning is typically used for dimension reduction. So like, let's say you have a data set that has like 100 dimensions, let's say, and you want to break that down to like 5 dimensions. So you want to combine those 100 dimensions together to make 5 dimensions. This is where unsupervised learning is useful. So for dimension reduction, so there's a group at the NRC that used deep learning to help design a grading coupler, and they actually used dimension reduction to make the problem a lot easier. And similarly, clustering. So if you have a bunch of data, like a bunch of things that you want to sort, but you don't know how to sort them, you can use the clustering algorithm and it'll find clusters in your data set. And finally, reinforcement learning. So I know it mostly for game AI. Robot navigation is another one, real-time decisions. So reinforcement learning is kind of the future of AI. For today, however, we're going to be focusing on supervised learning because this is the main type of learning that you will use in the real world or in physics and research. Because a lot of what we do is inputs and outputs. If you're in the lab, for example, you have a laser and you want to know the effects of the intensity of that laser. So you take a measurement with one intensity, you take a measurement with another intensity, take another measurement with another intensity. And so you have a list of intensities versus spectral data, let's say. So input, output. So that's why I'm focusing on supervised learning. It's also what I typically use. Supervised learning, it's all just glorified curve fitting. That's was what I realized when I started learning machine learning 3 or 4 years ago. So as I mentioned, there are 2 types. There's your regression and your classification. So here's kind of it represented pictorially. So let's say you have a bunch of data points and you just want to fit a line to it, that's regression. In this case, it's linear regression because it's a straight line. Or if you have a bunch of data points and you don't know how to sort them, classification. So the computer actually labeled these dots as 0, 1, 2. So it found 3 clusters. So I'm going to start off with regression, and we're actually going to cover the following. So we're going to cover linear regression. We're going to cover how to do cross-validation with that. We'll also be doing a bit of polynomial regression. We'll then go on to deep learning regression, where I'll also start with a simple example, and then we will dig into that data set that I attached. And finally, we're going to do some deep learning classification. So we're going to classify handwritten numbers. So the goal is to take these handwritten numbers and label what is that number? You know, so you'll see someone hand drew a 1, and you want the deep neural network to tell you that that is a 1. I guess in theory that shouldn't be on this slide, but oh well. All right, so regression steps. First, you need to generate or acquire your data. And in this step, you kind of want to also know your data. So I recommend plotting it. Step 2 is data engineering. So normalize your data. Typically, people will normalize your data between 0 and 1 or -1 and 1. You want all of your data points to all be within the same order of magnitude. So let's say that one of your inputs is wavelength and the other input is the refractive index or something. And you want to, the output is, let's say, a spectrum. You want to normalize your wavelengths because your wavelengths are going to be, let's like 100 nanometers, let's say. So 10 to the -9. Whereas the refractive index is between 1 and 4. So you want to make sure that your numbers are all within the same order of magnitude. So you'd want to maybe make your wavelengths in microns instead of nanometers or instead of meters. Anyway, so that's data engineering. You want to split your data into testing and training data. So you will train your machine learning algorithm with the training data, and you will test with the testing data, because you want to make sure that your model has never seen the testing data before to validate how accurate it is. Finally, you train your algorithm using the training data, and you test your algorithm with the testing data. Okay, so first thing we're going to look at is the simplest kind of machine learning. If you ever pick up a machine learning book, this is chapter 1. It's linear regression. And we've all done this. We've all had to, we were all in the lab at one point, fitting lines to data. So you guys kind of know what this is. You assume that your output y is equal to some sort of weight, a0 multiplied by your first input, plus another weight, a1 multiplied by your second input, x1, and so on and so forth. And there are 2 ways that people would do this. Ordinary least squares is kind of the most common way. So that's where you use like linear algebra, and you have to like invert a matrix to find out what the line of best fit is, or a gradient descent, which is kind of the more machine learning way to do it. With Scikit Learn, the way that we're going to do this is using ordinary least squares, but I'll discuss gradient descent a bit later on. Okay, so we're going to now go to our first Python script, our first simple example, where we're just going to generate a data set. So we're going to have our inputs are going to just be a list of values between 0 and 2 pi, and our output's going to be the sign of that input. And we're going to do linear regression on that data. So now what I'm going to do, I'm going to pull in, I use the Spider IDE, which comes with Anaconda. Jesse is probably mad at me for this, but I do use this. Oh my God, go. Why aren't you moving? Oh, that's why. Sorry, guys. So Spider can be mean sometimes. Hide this message. Why can't I hide this message? Dismiss. All right. Crap. Hold on. Oh man, my IDE is it's frozen now. All right, I have to Control-Alt-Delete, and sorry guys. And task. Well, that's not fun. By the way, guys, be sure to like kind of pipe in and like stop me if I'm going too fast at any point. Hopefully what I've shown up to now is nothing too huge, nothing too confusing to understand. Okay, so now I'm going to reopen up Spider. Have any of you guys used Spider before, like the Python IDE? Right, Ryan has. Sorry, Evan, you're covered by like my Spider opening screen. Okay. All right, now then, hide this, dismiss, there we go. Pull that into there. All right, share screen, and boom. There we go, you can now see my Spider IDE. I'll now go in to here. I don't think there's anything crazy in here. And I'm just gonna open up all the machine learning workshop Python scripts. Again, you guys have access to these same scripts. They're all on the link that was sent into your email or will be posted underneath the YouTube video. All right, so remember that step one is to generate our data and to plot it. So here I generated the data. Oh, so yeah, I'm on machine learning workshop, ML workshop _ linear. So you want to import first your numpy module and your matplotlib module. Again, it's assumed that you know numpy and matplotlib in this tutorial. So I'm going to F9 that, and then we're going to generate our data. Okay, so here X is just a linspace from 0 to 2 pi with 1000. You need to reshape it. So this dot reshape -1, 1, which will make it a 1000 by 1 array. If you don't do that reshape, Scikit Learn gets mad. Okay, so I'm going to uncomment this plot function here, and we're going to plot the data. So yeah, it's just a sine function. We've all seen that before. Data engineering, so I'm going to normalize all the data. So I'm going to normalize it so that everything is between 1 and, well, for the x's will be between 0 and 1, and the y's will be between, well, -1 and 1. So the y's don't really change at all, but still normalizing the data. Next, we're going to split our data into testing and training data. So we're going to do a 30-70 split. So 30% testing, 70% training. And the way that I do this is I use this train test split function that comes from Scikit Learn. So you can call it from scikit-learn.model selection. And you basically, the outputs are going to be 4 arrays. There's going to be the X train array, the X test array. So those are the inputs for the training and testing set. And then there's the Y train and the Y test. So those are the outputs of the training and testing set. You have to give it your X and Y values as inputs. So I give it the normalized values. And you tell it how big you want the test to be. So I said 30%, so that's 0.3. And you give it a random state. So it'll randomize the data. It'll actually even shuffle the data a bit. And I like to, you don't have to give it a random state, but I like to. So like if I'm going to use 42 here, but like I could also use 12. But if I want to recreate the same process over and over again, it's good to have the same random state. So I'll keep it fixed there. So we'll do that now. Go ahead, Ryan.
So what is like the benefit of having a random state?
It just makes it so that every time you do this train test split, you get the same data in the training and testing sets.
If you don't write that, then it just picks some sort of random state on its own. Okay.
Exactly.
Okay.
It generates the random state randomly. Yeah.
Okay. Cool.
Yeah. Okay. So if I F9 this, it takes a second, but now our data is now split into testing and training data. Okay. One thing that I do here is I actually, so because this function does 2 things. First, it shuffles your data around. So it like, you know, if you plot, actually, if I just plot X train, plot X train, you'll see that's no longer a straight line. It's actually chaotic. Before it would have been a line from 0 to 1 or 0 to 2 pi, depending on how you normalized. But now it's shuffled. So for the testing, for the point of testing it later on, I want to unshuffle the testing data. So I do a numpy.arg sort of the X test, and I use those as input. I basically rearrange the X test and Y test so that it is now back in order again. So if I plot X test, you'll see that it's going to be just a straight line, or, you know, sort of a straight line. Okay, so next we want to train our algorithm with the training data. So to do this, again, with Scikit Learn, it's super easy. You just call, you import linear model from Scikit Learn. So I'm going to F9 that. And then you have to define the model object. So you do that by saying model is equal to linear model dot linear regression. So there, underneath linear model, there's a bunch of different linear models you can choose from, but they're all kind of various forms of linear regression. And once you have that, you just fit your model using model.fit X train, Y train. It's that easy. So if I do this, F9, so now it's going to approximate our function as a0 times x input. So it's going to be a line, and you could actually figure out what that a0 is by asking for model.coef, model.coefficient. If I do this, it tells me that a0 is minus 1.94. So our sine function, if linearly approximated, has a slope of minus 1.94. And finally, we can test this by using the prediction method of our model. So just model.predict, give it the x test. And then I'm going to plot the x test versus prediction and the x test versus the actual data y test. So if I do all that, here we go. Here's our plot. So you can see this, the yellow line is our testing data, and the blue line is the linear regression, is the linear fit of that. And finally, we can calculate what the error is. It's going to be quite high. I don't know why I can't actually see. Oh, there we go. All right. And we can now calculate the error, and the mean percent error is 235%. So it's a high error because this is obviously not a linear function. Are there any questions about this script? Does it make any sense? Does it make sense to you guys? Awesome. All right, so let's go back to the PowerPoint. There we go. And I'm gonna keep it. Are you guys okay with me keeping it in this mode, not in presentation mode? All right, excellent. All right, so as a next step, the next step of complexity in our machine learning, we want to do polynomial linear regression. And so polynomial regression is just a generalized version of linear regression. So if you define your x not to be just one, just a constant, so that's kind of going to be like your y-intercept, let's say. X1 is equal to x, x2 is equal to x squared, x3 is equal to x cubed, and so on and so forth. We can actually use our linear regression algorithm to, for polynomial regression. So the way that we can actually generate these x squared, x cubes, all that stuff, using the polynomials feature method from Scikit Learn. So all that does is that you give it an x, and it'll give you a list of 1, x squared, x cubed, all the way up to whatever degree you input. If you have multiple inputs, that's also no problem. So if you have x1 and x2, it'll actually generate polynomials with respect to both inputs. So 1, x1, x2, x1 times x2, x1 squared, x2 squared, all the way up again to the nth degree. So now we're going to repeat polynomial regression using the sine function. And we're going to add a bit of noise this time around. So let's go into our Python script. We're going to go, so the machine learning workshop _ poly is what we're working on now. Okay, so what we're going to do is, again, we're going to generate and plot our data. So our x's are the same, it's just from 0 to pi. All right, and then I'm going to generate some noise. I do that using the numpy random module. And then I'm going to plot y, so we're going to have y is equal to sine x plus noise, and I'm adding 2. And there's a reason for that. So plt.plot x, y. So here we can see we have a noisy sine function. And I added 2 so that it's going to, every value is above 0. So that way, when we calculate our mean percent error later on, because we have to divide by y in that mean percent error calculation, I don't want to divide by 0. So that's why I'm doing this. That's why I'm adding 2. Again, that could be seen as kind of data engineering, but anyway, we're going to normalize our data again, F9. And now we're going to make those polynomial features. So we do go from Scikit Learn .preprocessing, you import your polynomial features method, and then have to create the object. So poly is equal to polynomial features. You give it the degree you want. So I say up to 15 degrees, let's say. Done. And then to create the actual polynomial values, to create your 1, x squared, x cubed, you have to say poly x, or whatever you want to call your x, is equal to poly.fit transform normalized x. So just take that normalized x value, put it in there, F9. And so if we had to look at poly x, you can see now we have a much more complicated array. In fact, if you look at the shape of it, it is 10,000 long, so that's the 10,000 data points, by 16. So that's the degree, 15 plus 1 for the 0th degree. All right, now we're gonna, again, split our data into testing and training data. We did that before. We're gonna resort our testing data like we did before. A bit more complicated this time because there is an extra dimension to our inputs. But you should be able to follow that. And finally, we're going to train using linear regression again. This SGD regressor, we'll talk about that later. For now, we're just going to use linear regression. So I'm going to do this. And here I also outputted the coefficients again. So now there's a lot more coefficients. There's actually 16 because there's A0 all the way up to A16 for the 16 different powers of X. And so now we're going to do our prediction. And we're going to plot our predicted versus the actual data. And here you go. We can see that our prediction was able to find a really good line of best fit for our data. It almost looks like a perfect sign function despite the randomness. And our mean error is 54% because obviously the randomness adds to the error a bit. Does that make sense to you guys? How all that worked out? Are there any questions? Am I going too fast? Cool. All right. All right, so now there's a concept that I want to get into about overfit. So we're going to go back to the script quickly, and I'm going to go up to this polynomial features. So we went up to degree 15 here, but I want to do something ridiculous. Let's do the 51st degree. Let's try that. So we're going to redo all of this stuff again. Okay, so you're going to see something happening here. You can even see here that the yellow line here is now it's quite a bit less clean. It's a lot more wobbly. And in fact, if I go up into an even higher degree, so let's go up to the 101st degree. F9 that again. Okay, well, it's equally more wobbly, but I was expecting it to be a lot more wobbly. Anyway, the reason why the line is wobbly here is that we are overfitting. So with 15 degrees, we saw that our prediction was nice sine curve, which is what we expect it to be. So the sine curve plus these wobbles means that it's trying to fit to the randomness as well. And you really don't want that. So that's the concept of overfitting. So if your model is too complicated, you might be overfitting. So overfitting is when you have too much of a good thing, my own quote. So here's a cool plot, a good plot for this. So let's say your data set are these dots, and this is your line of best fit. This is underfitting. You can't make a good prediction off of this line of best fit. So that was the case with the sine curve and the linear regression. That line, that straight line, is not a good approximation to a sine curve. Of course, unless you're close to 0. A good fit would look something like this, where the line isn't touching each point, but like you can see the line follows the trend quite well. However, if you make your model too complicated, you might overfit. So this is what overfitting looks like. So it's like trying to hit every point, but this is not a good approximation, right? Because if you try to extrapolate, so if we try to go beyond the time of our data set, this line here will tell us, well, it's going to keep going up probably. Well, this one here is going to tell us, oh, it's going to go down, right? It's not a good fit. So that's what overfitting means. And to kind of take care of that problem, we typically use a process called cross-validation. And the most common type of cross-validation is called k-fold cross-validation. So we're gonna redo our process here, and we're gonna change step 4. So steps 1 to 3 are all the same. You generate your data, know your data, plot it, do your data engineering, split into testing and training. But step 4, instead of now just going right to training our data. Oh, there's a chat. Oh, Okay, I didn't see that. Okay. Should I look at this, Daniel?
If you want.
I'm good. I'll keep going with this. I'll look at it later. All right. So you want to use cross validation to kind of like find the best algorithm, to find the algorithm that doesn't underfit but also doesn't overfit your data. And finally, you want to test your model again. So k-fold cross validation. It's a bit tricky. It's hard to explain, but hopefully this makes sense. So first thing you do is you're going to split your training data. So again, we've already split our data into training and testing. So we're going to take our training data and we're going to now split that into k subsets. So that's where the k-fold cross validation comes from. You split it up into k subsets. You then train your model on k-1 of those subsets. You then validate your model, or you test it on the kth subset. And then you repeat steps 2 and 3 for all subsets. So by the end of this process, all subsets have been used for testing. And at each subset, you calculate the error of, you calculate kind of the mean error of that kth subset in the model. And the total error of your model is just equal to the average of all those errors. So hopefully that makes sense. Here's a kind of a pictorial way of looking at it. So you have your training set here, and you split it up into, well, here they're doing k is equal to 10, so they do it for 10 folds. So the first iteration, you train with these 9 gray boxes, and then you test with this blue box. Your second iteration, you train with these 8 plus this one, so that's 9. Test with this guy, so on and so forth, each time calculating the error. And finally, the error of this network is just equal to the mean error of all, the error of this model, sorry, is just equal to the mean error of all of these guys. Does that make sense to you guys? Good? All right.
I have a question.
Sure, go ahead.
So pictorially, sorry, I think I missed it. The blue box is what's being predicted based off the 9 other white boxes here?
Well, you're taking, so you're kind of taking that blue box here, that blue subset, as the testing set for this iteration. So like you're taking the the inputs of this test part, this test subset, and you're inputting that into the trained model. And then you're taking that output and you're calculating the error of that output with respect to the y of the test set. Maybe there's a better way I can explain that. Yeah, you're just comparing the output of the model for this subset of data with its actual data, and you're calculating the error between the two of them. Does that make any sense? Okay.
I think I understand. You're using the 9 white data subsets in each iteration to test, to make a model that predicts the value for the blue shaded subset.
Exactly, and then you compare, okay. you test how well it did on that blue shaded subset.
I see.
And the reason why this works is that it gives the model a chance to kind of sample all of the data, to do a test on all of the data in the entire data set. And this typically will catch any sort of overfitting. So it'll actually give you a high error if you are overfitting your data. And so in case you didn't understand it, don't worry, there is a Python script where we'll do the same thing we did before. So the sine curve plus noise for polynomial regression. Well, we're going to do this now with cross validation built in. Okay, so you'll notice that these scripts are getting longer. So now we're going into this machine learning workshop _poly cross validation. So a lot of the things here are the same. So again, the data set is still the same thing. I'm going to add 2 again. So I added 1 here, add 2. Okay, so we plot their data. The randomness is a bit less on this one, actually. So, oh, it's because I multiplied by 0.5. So let's not do that. Oh, that's better. And we're going to do some data engineering. Now we want to So we're going to do cross-validation, and we're going to do it with respect to the degree of the polynomial. So I created a list here of degrees. So I'm going between a polynomial of degree 2 all the way up to a polynomial of degree 101. I'm defining a list called error tracker. And I'm now going to loop through each polynomial degree. So for D in degrees, so for the first iteration, D is going to just be 2. For the second iteration, D is going to be 3, so on and so forth, all the way up to 101. Okay, so for the second degree polynomial, let's say, we're going to call our pre-processing polynomial features method. We're going to generate those polynomial features like we did before. We're going to split our data into testing and training data like we did before. And right, then we sort our test set again, as we did all those times before. Now this is where the cross-validation part happens. So we're going to call sklearn.model selection, and we're going to import from there kfold. So that's the kfold cross-validation function. And we're going to import our linear model as well. So I'm going to set k is equal to 10, like was in the picture here. Okay, so we set k is equal to 10, and we then call k folds for the n splits equal to k, or 10. Now we're going to loop through these k subsets. So the way you do that is you have this for loop. So for train index and validate index in k-off.split x train. So what does that mean? So here, this is our kf. So this is an object, and we're going to call this split is a method of that object class. My terminology is a bit rough here. But what kf.split is doing is it's taking our training data and it is splitting it into 10 subsets. So for each iteration of the loop, this function here will output a list of indices corresponding to the training data for this loop and the validation indices for this loop. So essentially, it's creating those subsets, those 10 subsets for us. We don't have to worry about it. It's doing it all for us. And all we have to do is just create this loop. And so then, so X train cross validation is just X train for the train index. Okay, and then the validation set for this loop is just the X train at the validation index. And similarly, we have to do the same sort of splitting with the Y train and the Y validate. So again, in this situation, X train are just going to be like the training indices are these white boxes, and the validation indices are the blue box. And again, with each iteration of this loop, the train indices and the validation indices are going to swap each other out. Hopefully that makes sense. So we're going to then train our model on the X train CV and Y train CV. We're going to make our prediction using the validation set, and we're going to calculate the error with respect to the validation set, which is here. And then we're going to update our total error by adding that error to it. And in the end, we're going to calculate the mean error by just dividing total error by k. So all of that, this code here is just this slide here, up and including the error. So error is equal to 1/10 times the sum of all the other errors. So that is k-folds cross-validation. So if I click run, it's actually going to do this cross-validation, and I'm actually going to be plotting the error tracker. So I'm going to get a plot where it tells me the error as a function of the degree of the polynomial. So I'm going to run this now. Hopefully it doesn't take too long. It's there we go, perfect. So this is a really good demonstration here. I'm going to make this plot even bigger so you guys can see it better. Here, big size is equal to, let's go to 10 by 10. 10. And I'm just going to F9 that. Here is what our this is what our error looks like as a function of degrees. I realize on this screen, this is like my big screen, but like Spider looks terrible in it. So I'm sorry if the plot's a bit pixelated here. So what you have is the y-axis is your percent error, and the x-axis is the degrees, and it goes from 0 to 100, or sorry, it should go from 2 to 101. So you can see that the error for the second order polynomial is super high, and it goes down for the third order polynomial. And for up until about the 30th order polynomial, the error is quite low. Here you can see where it starts to overfit the data, right? Because here the error starts to go up for higher orders polynomials past, say, 30 degrees, past the 30th order polynomial. Does that make sense? So you can actually see underfitting on the left-hand side of this plot and overfitting on the right-hand side of this plot. And your kind of sweet spot is in the middle here. Go ahead, Ryan.
So one thing that's interesting is that you get specific values that that come back down to, you know, this sort of standard error that we're getting.
Yeah, yeah.
Have you ever looked into that in general? Like, I mean, like, is there something that's kind of interesting about sort of the statistics when it comes to?
No, I haven't looked into this, so I don't know. I don't know if anybody's studied.
Sorry,
I mean, there's probably
a little bit of random question.
Yeah, if you go, there's probably papers from like the 90s where like people study like the statistics of cross validation, but no, but I personally, I don't know.
Okay.
That is a good observation.
Yeah, it's
But
just like there's a lot of projects that I've seen recently that they have these sort of like random jumps in that, and then you can kind of pick your sort of plateau in there. So it seems like, I don't know. I mean, it definitely system dependent, but it's just cool. Yeah. Sorry for the random tangent.
Oh no, it's okay. That's good. That's awesome. But yeah, what this plot tells you though is it tells you where you're underfitting and where you're overfitting. So it gives you kind of a nice good range. And usually you would pick the smallest error. So well, let's find out what is the smallest error. So I'm going to use the numpy argmin function, argmin of error tracker. So it's 4 series. I don't feel like doing mental math. So that's a 6th order polynomial is the best one according to this. So that's the model that I would use to fit my noisy sine function. Okay, so hopefully that made sense. I'll now go back to the PowerPoint. Okay, so here's that same plot again. Really a lot easier to see here. Okay, it's not the exact same plot. It's slightly different, but you can see the same trend here. You have some underfitting of your model for the low order polynomials, and you have some overfitting for the high order polynomials. And so the optimal models would be, well, in this case, it was around 8th order and like the 15th order polynomial. Okay, so moving on. So now I pose a question, is linear regression machine learning? And I kind of gave away the answer earlier. So my answer, and it is subjective, it depends on how you train it. So if you're using ordinary least squares, which is what we are doing, when you use Scikit Learn's linear model, when you use the linear regression module, you're doing ordinary least squares, which is why it's so fast. It's why it's able to train really quickly, because you're just inverting a matrix, I think. I forget how ordinary least squares works, but I believe it's just inversion of a matrix. So this I don't consider to be machine learning, because it's just using linear algebra to get the line of best fit. If you were to train it using gradient descent, this is what I would consider to be machine learning, because you're using an iterative algorithm that seeks to minimize the error. So you're basically at each iteration of the training process, you're updating those weights, so your A0, A1, A2, in such a way that it is reducing the error between your output Y and the actual sine function. The output Y, sorry, the prediction of your model with respect to the actual data itself. So ordinary least squares is just invert a matrix and you got it. Gradient descent, you're actually like, the algorithm is actually learning what A0, A1, A2 should be to best model your data. Now, the reason why we use ordinary least squares though is because it's perfect. It's the best, there's a line of best fit. gradient descent is usually there's a bit of stochasticness to it. There's stochastic gradient descent is what it's usually called. So there's a bit of a random state where it starts at. So the endpoint actually depends. It'll actually change every time you click run. Okay, so if you want to use gradient descent for this linear regression problem, you just have to uncomment what I have commented out here, and you just call linear model, same module, and SGD regressor. So that's stochastic gradient descent regressor. So that's kind of the linear regression version of, well, that's kind of the machine learning version of this linear regression function. And so I'll actually run this and we'll see how well it does. The first thing you'll notice is that it takes a lot longer because it's not just inverting a matrix. And you can see it's actually not that great. It doesn't do as good as a job as ordinary least squares. So that's something you can play with. You can play with, so with the SGD regressor, there's a lot more knobs you can turn. You can actually go to the Scikit Learn website and look, and you'll see there's like a gazillion inputs for this thing. But here I said like maximum number of iterations I want is 10,000. So it'll do maximum 10,000 training steps. And I want a tolerance of 0. I don't know how many zeros this is, but, and it does its best. And as you can see, its best isn't that great. Okay. Yeah, okay, so this is what I just said here. So you just use SGD regressor. It takes longer to train, it's less accurate, and there's a lot of options for you to play around with. So other machine learning algorithms, so you can actually find this chart on the Scikit Learn website. But I love this chart so much because it literally, it's a flow chart. It tells you based off of what data you have, what you want to do, it'll tell you which algorithms to use. So you start, if you have, do you have more than 50 samples? Yes, you can keep going. If no, get more data. I mean, perfect. If you're predicting a category, then you're going to go into a classification algorithm. If you're not predicting a category, if you're predicting like a continuous values of numbers, you go into regression. And if you're in regression, there's different things for you to use. So yeah, this is a really good chart. And this PowerPoint will be made available after the presentation. It'll be in the same folder where all the Python scripts were. Okay. So now we're going to move on to deep learning. This is a huge jump. If you pick up an intro to machine learning textbook or whatever, a lot of them, if they're any good, will cover deep learning at the very end, where like the first, 9 chapters are, linear regression, polynomial regression, logistic regression, which is not actually regression, it's classification, but that's not important. It'll cover actually probably most of these algorithms that you see on here. But because you guys are here probably for deep learning, we'll cover deep learning. So deep learning is kind of like regression, like normal regression and classification algorithms, but instead of using functions to fit your data, you're using deep neural networks. So this is a deep neural network. So you have your input layer. So you input your values in your input layer. So here I have 2 inputs. And then these layers are all connected to this next layer, which is called a hidden layer. And then all the nodes of this hidden layer are connected to this next layer, which is the second hidden layer. And finally, we have some sort of output layer. So it is considered to be a deep neural network if there is 1 or more hidden layers. If there are no hidden layers, you're basically just doing linear regression. I'm not going to go into how that is, but maybe you can figure it out on your own afterwards. So how deep learning works is it's basically just a bunch of linear models connected with a slight nonlinearity added in. Sorry guys, I stutter sometimes. Okay, so here I'm going to zoom in on these 4 nodes here. So the inputs and 2 of these hidden layer nodes. So that's what you're seeing here. So what happens inside this node is that it takes the values from the previous layer or the input layer, as I show here, and it does just a linear fit to it. So it calculates some y, and that y is just a linear combination of the inputs, so x0 and x1. The output of this node is going to be some sort of function f of y0. So the output of this node is essentially just a function of the linear combination of the previous layer. Does that make sense? Okay, similarly, all the other nodes in this layer will have the same sort of thing, except for different weights. So here it's A0, A1, here's B0, B1, and the node down here would be C0, C1. And you can think about training a neural network as figuring out what this A0 and A1, B0, B1, C0, C1 are, like what those values are to best represent your data. So this function here, this f, is called the activation function. And its purpose is to add nonlinearity into the neural network. So if you were to just output y0 out of these neurons, sorry, these nodes, these circles are called neurons. I should have said that before. If you were just to output y0 and y1, this would just be one gigantic linear model, because you're just adding up linear combinations of everything. And in the end, you're just doing linear regression. So this f function acts as a nonlinearity, and it's called the activation function. And there are different types of these activation functions, but they're all kind of what we call threshold functions, in which, it's kind of flat and then something happens somewhere. So here, the first one we see is the sigmoid function. Again, it's flat, and then it goes up, and then it goes back to being flat again. Tan-H is very similar. ReLU is the most common one that I've seen used. So ReLU is basically, it's 0 all the way up to x equal to 0, and then it's just y equals x above 0. Leaky ReLU, which kind of similar, but leaky on the negative side. Max out, never seen it before. They didn't plot it, who knows? And then there's LU, which is kind of like leaky ReLU, but a bit flatter on the bottom there. So in this presentation, in the scripts that I gave you, we're all using ReLU. Go ahead, Ryan.
So, I mean, okay, each neuron is some sort of linear function, or kind of like a polynomial of that, but like, is it that like each other neuron that's in that given like line is like a perturbation on the other neurons in a sense?
Is a perturbation on the other neurons.
Like you said, it's like a nonlinearity. Well, it is a nonlinearity, but I'm just kind of thinking about how this nonlinearity is interacting in the system. Okay, this is gonna be kind of a little bit side thing, but you've done tight binding model?
I haven't,
Okay.
but I know of it.
Okay. Anyway, so you have a central atom, and then you have every atom beside it has a little bit of a perturbation onto that one specific atom.
Right,
place.
and you only care about the atoms on either side of it, right?
Yeah, exactly. I mean, each one of them is like a smaller sort of perturbation, but so is that kind of analogous here, where it's like the neurons will talk to each other, or is it completely separated?
Oh, I see. I would
Is the
say
nonlinearity like crosstalk in a sense?
no. So the nonlinearity of each of these, so the nonlinearity is purely this activation function.
Okay.
So like without the activation function, everything is just going to be a linear sum of x0 and x1. Like this layer will be a linear combination of x0 and x1. This layer here, despite the operations applied here, because all these operations were just linear, you output these into here, these will all be linear as well.
Yeah.
And in the end, your y0 and y1, your outputs are just a linear combination of x0 and x1. So the activation function just kind of acts as a way to give you a nonlinearity. So no, it's not like a tight binding model in that sense.
Yeah, sorry, it's just the one thing that came to mind to think about this, but okay, cool.
No, it's good. Like maybe I'm not seeing your analogy correctly, which is definitely possible. Like we definitely we all see things in a different way. We all connect to what we're learning in different ways.
Yeah, for sure. All right, cool. Sorry about that. Thanks.
Oh, no, no worries, no worries. Actually, it's an interesting point, is that typically before you train your neural network, these your weights, these A0s, A1s, B0, B1, those are what you're training for, but those are usually set to random values to start with. And depending on what random values you start with, that actually affects what the trained network will be. So depending on, and you can think about this in a human way by thinking like, depending on your background, you will be trained differently. Your brain trains differently. But hopefully, independent of the inputs, independent of the starting point, independent of where we all come from, we all get the same answer in the end. Ideally, sorry. Okay, sorry, Ryan.
All good, all good.
Yeah. All right, so how do you train a neural network? How do we calculate what A0 and A1 and B0 and B1, how do we calculate those weights? So this is a long and tedious process to teach. So I'm just gonna give a really quick and brief overview of how this is done. So it's done in 3 steps. So step 1 is forward propagation. So you send in all your inputs and you compare your predictions, so your outputs, to the actual output of your data, to the actual data, and you calculate whatever the error is. So here I give the squared error, which should be, I guess, the mean squared error, but that's all right. Next, you do backwards propagation. So this is a step that is difficult to understand, but you essentially are calculating the gradients of all of those weights with respect to the error. So here we have the derivative of the error with respect to A1. So that was this weight over here, let's say. I should have used A0 and A1 instead of A1 and A2, but whatever. Actually, I can fix that right here. A0, and you calculate the derivative of the error with respect to A1. And you do that for every single node in your network, every single weight in each of those nodes. And everything in your neural network is differentiable, right? Because here, let's take a look. Y is just a linear combination of X0 and X1, right? And this output is just a function of that Y. And those functions all have functional forms. They're all different. Everything here is differentiable. Your neural network is differentiable. You can actually take the derivative of your error with respect to all of those weights. And this is done using just a really long chain rule. And it's done backwards. So first you would calculate the gradients of these nodes, the gradients of the weights in these nodes, and then you would use those gradients in a chain rule to calculate the gradients of the weights in these nodes, and et cetera, et cetera, et cetera. That's why it's called back propagation. You're going backwards. Modern day machine learning languages have auto differentiation built into it. So these gradients can be calculated automatically. If you're interested in that, you can go down a rabbit hole in auto diff. It's really cool. But finally, you then update your weights. So you have your gradients, and you're just going to use gradient descent or something similar to gradient descent to calculate your weights. So this is what gradient descent looks like. So your A1 new, so your new A1 weight is equal to your old A1 weight minus some factor gamma multiplied by that derivative. And if you do that, if you repeat this process multiple times, your weights will tune themselves to minimize the error. That's what gradient descent does. So hopefully that's a good overview of how we train a network. Yeah, so you do this for as many iterations as you need until all your weights converge. So typically the neural network will train until like the error kind of stops changing. Good news, with Scikit Learn, all that's done for us. With any sort of machine learning library that you might use, the back propagation and like the training process of a neural network is built into it. So you don't have to worry about programming that yourself. But like I've seen somebody do it, like I've seen someone actually write the code to do that, and it's heck. Like I wouldn't recommend trying that yourself. All right, so how to make a deep neural network in Scikit Learn. This is what we probably all came here for. You first need to decide on your neural network architecture, so the shape of your network. So for example, this network here has 2 hidden layers, each with 3 nodes. So that's the architecture. So for example, if I want a neural network with 5 hidden layers, and in the first hidden layer, I want 20 nodes, second hidden layer, I want 30 nodes, the third hidden layer, I want 40 nodes, then I want 5 nodes, and then I want 3 nodes. All right, that's choosing the architecture. Next, you decide on your activation function. So when in doubt, use ReLU, or if you have the option, leaky ReLU also works well. So for regression, though, ReLU is great. If you're doing classification, you might want to look into sigmoid or the 10H. And then you decide on an optimizer. So when in doubt, use Adam. Adam optimizer, which is like adaptive gradient descent or something like that. I forget what it stands for. And then you set up, so this is how you set up your neural network is here. So we chose our neural network shape. So there's 5 hidden layers. So I'm going to have 5 values in the neural network shape tuple. This is a Python tuple object. And here, as I said, I want 20, 30, 40, 5, and 3 nodes in each of those layers respectively. And 20, 30, 40, 5, and 3. I decided on my activation function to be ReLU, my optimizer to be Adam. And then you just need to call the Scikit Learn machine learning MLP regressor MLP stands for multi-layer perceptron. That's another way of calling a network. Go ahead, Ryan. You can just interrupt me.
Yeah, sorry. I have way too many questions all the time.
It's okay. It's okay.
What are there any physical systems that follow this ReLU regression type behavior?
Oh, that's a good point. I didn't mention this before, but I have it in the slide. All of these activation functions, I call them threshold functions because again, they're flat until something happens. And that's actually based off of neurons. So that's the action potential of a neuron. So a neuron only fires when a certain voltage is reached, right? So the kind of like a potential builds up, and when it gets to a certain point, it then fires. And that's what this kind of represents. Right. So I didn't mention that before. I got distracted, but
yeah, because I've seen a lot of these other behaviors in that, but I like ReLU is just like, 0, and then it has this linear function, which seems like there should be some sort of physical system, but
yeah, another the work function of material. So what's the photoelectric effect? Same thing. For a specific frequency, you start to see photoelectrons.
Okay, cool.
Yeah.
Awesome.
Yeah.
Thanks.
No problem. Right, so you define your shape, activation function, your optimizer type, and you just put those into the Scikit Learn deep neural network function. And you then again, like before, dnn.fit x-train y-train, that's it. That's what trains the neural network, is just dnn.fit. It's beautiful. You don't have to worry about back propagation, all that stuff. It's good to know what's happening, but you don't have to worry about it yourself. So now we're actually going to do this. We're going to, again, go back to our sine function with noise, and we're going to now fit a deep neural network to that sine function. So let's open this up, and we're going to go to machine learning workshop, ML workshop _ deep learning. It's a much shorter script than everything else. So again, we generate our data and we plot it. Done. We normalize our data as before. Oh, okay. Stop. Oh my God. There we go. We then split our data into testing and training data as before. And we define, so I define the neural network shape here. So I have a neural network with 3 hidden layers and 100 nodes per hidden layer. Let's go with actually 100, 230, and 40. I don't know. It's up to you. And then you just got to make sure you put these guys in your neural network regressor. Oh, yeah, I guess I called that up here. So I'll bring that. Oh, here we go. That's up here. So it's from sklearn.neural network import MLP regressor. Okay, so then we're going to do that. So we define our neural network. Oh, that's because I didn't do this. There we go. Sorry, guys. I am getting sloppy. And then we fit our neural network. That's going to take a bit of time. Oh, okay, it didn't take too much time, actually. So you can actually see it fit. So it tells you, so it took 65 iterations to fit. And you can actually see what the error is as a function of iteration. So you can see the error actually decreases. And finally, we can now do a prediction. So we take our X test and we do dnn.predict, F9 that. And finally, we're going to plot the prediction versus the actual data. And you can see that the neural network, blue line, this guy here, it did an okay job. It got a sine function, sort of. So you can play with the neural network architecture to get the best fit. You know, let's say if I did 10, 23, 40, is that any better? No, I mean, it's less hidden layers. In general, the more hidden layers and the more nodes, the better your fit's going to be. But be careful, because if you take too many hidden layers and too many nodes, not only will your training time increase a lot, you'll also start to overfit your data. So you got to be careful with that. So kind of, I guess, homework. I mean, not like I'm going to check, but you know, try to do cross validation with your neural network. So go through, like, you know, loop through different architectures and see if you can find the best architecture that doesn't overfit or underfit your data using cross validation. It's not that hard. I mean, I say it's not that hard because I've done it. If I can do it, anybody can do it. So hopefully that made sense. That's literally it. That's training a neural network. But that's boring because it's just a sine function. So let's do something a bit more interesting. So here's kind of the first complicated example, which means that we're getting close to the end of this presentation. So we're going to do an example based on me scattering. So I'm an optics and photonics guy. Has everyone here heard about me scattering before? Has anyone not heard of me scattering? Okay, that's all right. So me scattering is just a solution. It's just a solution to Maxwell's equations for a plane wave of light hitting a sphere. So here's your geometry, right? You have a plane wave of light coming in. It hits some sphere of radius A. The sphere has a refractive index n sphere, and it's embedded in a medium with the refractive index of n outside. And you want to know how much light gets scattered. What's the scattering spectrum of the sphere? And so that's what me theory is. Me theory is just the solution to this problem. So yeah, it's a method for solving electromagnetic scattering from spheres. And it's actually, the math itself is, it's accessible for a graduate student in physics, I would say. But there's also plenty of me theory calculators out there where you can like download code to do it. I have my own script that does it, that I generated the data set on. And that data set is on the Google Drive as well. So click on the link and you'll find it there. And if you're interested, I posted a link here to a pretty decent me theory calculator web app, which I did not use for this. Okay. Yeah, so as I mentioned, I generated a large data set of scattered, so it's the scattering spectrum, or also known as the scattering efficiency spectrum, for dielectric nanospheres with radii from 20 to 200 nanometers for wavelengths in the visible and IR, so that's from 200 to 1000 nanometers. So the data set has 63,125 data points, took about 2 minutes to generate, and each data point contains the sphere. So each data point represents a specific sphere. So it contains that sphere's radius, its refractive index, the refractive index of the ambient medium, a list of all the wavelengths, and the scattering efficiency spectrum for that specific sphere. So all of that is shown here. You can see all that. And the data is stored in a pandas data frame. So that's why I asked you to have pandas. So you don't have to worry about how to open up the pandas data frame. I have the code that opens it for you. But if you want to learn a bit more about pandas, there's a nice 10-minute tutorial right here. Pandas is a really nice way to organize data and to manipulate data. Okay, so let's go and look at the actual script. So we're going to get machine learning workshop _ deep learning _ me, spelled M-I-E. Okay, so this is it right here. So this time we're not generating data, we're actually loading the data into from our pickle file. So the data is stored in me scattering data.pickle. So you open it using this command here. Yeah, so basically what this, Oh yeah, you have to call the modules first. Basically what this pickle file is it's a pandas data frame, but pickled. So you can just reload it in and you load it in as a pandas data frame. So that's the beauty of pickle, if you were wondering. It just lets you store arbitrary data formats. You could actually also, you could store Python functions into pickle files. And you can unpickle the Python function. And anyway, I don't know why anybody would do that, but hey. Okay, so I've now loaded the data set. So I can actually just type, so it's under the title df. So df is the data frame. So if I type df into my console, you can see all the stuff here. So there are data points from 0 to 63,124, which I believe is what I put in. Yeah, 63,125 data points. Yeah. And you can see that there's the radius, there's the refractive index of the sphere, the refractive index of the outside. There's a list of wavelengths, and there's the corresponding scattering efficiency spectrum. And so if you want to see the columns, if you want to see like the titles of the columns in the data frame, you just got to say df.columns. If I F9 that, you can see the name. So radius, refractive index of sphere, refractive index outside, wavelengths, scattering efficiency. And if you want to see like the first few data points, you can just say df.head, and it shows you the first few data points. Okay. So I want to visualize a single data point. So all this code is to do that. Because we're running out of time, I'm just going to run this. You guys can go into this and try to figure out what it all means for yourself. But here, okay, I'm going to make that plot just a bit bigger. Size 10 by 10. All right, so here I'm taking data point 15. So to get that data point, I just had to call df.iloc index. I know it's weird to have to do that, but that's just how you access that data point. And it'll print out some attributes of that data point. So it says that this data point 15 has a radius of 10 nanometers. And a refractive index, refractive index of 1. I don't know what the outside refractive index is, but I can calculate, I can figure that out by just doing this and saying Ri, I believe it's outside. So the outside refractive index is 2.875. Cool. And this is the scattering spectrum. So here we have, as a function of wavelength, we have the scattering efficiency. I'm sorry that the plot's hard to see here, but that is the scattering efficiency as a function of wavelength. Okay, so now we have to do some actual data engineering. So I'm going to save all the inputs. So that's the radius, the refractive indices, and the wavelengths to a flattened array. So for one data point, the radius, there's going to be a list of inputs. There's a radius, the refractive index of the sphere, the refractive index outside, and all the wavelengths. Those are going to be the inputs. And I'm going to save them all in an array. So that's what this code does here. Okay, so if I just do this, we can see that now our inputs has a shape of 63,125. So that's 63,125 data points by 103 inputs. So that's the 100 wavelengths, the refractive index inside, refractive index outside, and the radius, 103 values. Okay. Next, we're going to scale all of our inputs. So we need to, obviously, we need to scale our wavelengths and our radius because those are in meters. So they're 10 to the negative 9 because they're all nano values. So I'm going to just scale all of those so that now they're closer to unity, closer to 1. Probably not perfect scaling. And I'm also going to have to prepare the outputs. So I'm just going to run this. And basically, this just creates an array called scattering that has all the scattering spectra in it. Now we go back to some more familiar things. We're going to split our data into testing and training data using this train test split function again. This time I have a test size of 20%. We can go with 30% like before. Do that. Okay. And we're going to define our neural network shape. So I don't know, I've played with this script a few times. since I uploaded it to the Google Drive, so it's not going to probably look the exact same as this, but I'm going to do 6, 7. I can't count. 7 hidden layers with 100 nodes per hidden layer, because it's a relatively large data set, so we can use a pretty large neural network. And yeah, I'm going to fit that now. And we'll see how long it takes. Yeah, so it takes a while. You can see here. So what I'm going to do is I'm just going to truncate it. So I'm going to say fit only for 10 iterations. So we don't have to spend the whole day waiting for this to fit. So yeah, for large neural networks, it takes a long time to train. So here you can see we're at iteration 3. You can see the loss is decreasing. So the loss is another word for the error. So the error is decreasing as the training goes on. And it looks like we're flattening out. Yeah, okay. So it is now finished. Now I'm going to do a prediction on the test set. So F9. It's pretty quick. Neural networks are really fast because they're just matrix multiplication when it comes down to it. And now I'm going to plot some of the data points. So I'm picking 11 of the test data points, and I'm just going to plot them all together. So it's not perfect, but here you can see, so this is the scattering spectra of different spheres. So the actual scattering spectrum is the blue line that you see, and then the yellow line is the deep neural network prediction for that corresponding sphere. And you can see that it does okay. It's not a perfect neural network, but especially for like these larger scattering spectra, it seems to do a good job fitting. But yeah, there's some noise here. So there's either some overfitting happening or some underfitting happening here. It's hard to tell. But you can play around with a neural network shape and try to find a shape that best represents the data. And finally, if you want to make an actual real prediction using just a entirely new particle, I'm going to now make a prediction for a nanosphere with a radius of 40 nanometers, a refractive index of 2.5. The outside is going to be vacuum, so the refractive index outside is 1, and wavelengths from 200 to 1,000 nanometers. And I just do that using this little bit of code, F9. And here is the predicted scattering spectrum for that sphere. Okay, and we're running low on time, and that's okay because I'm almost done. Finally, the last example is just a neural network used for classification of images. So here we're going to do handwritten numbers. So the goal is, can the deep neural network guess the integer that is handwritten? So here's what the training data looks like. So this is supposed to be a 0, this is a 1, this is a 2, this is a 3. They're heavily pixelated. I think it's like an 8x8 pixel image of these different numbers. So there are better data sets like this. So there's the MNIST data set, which you can download from pretty much any machine learning library, which has much higher quality numbers, but it's the same thing. It's just handwritten numbers, and you have to get the neural network to predict what the numbers are. Okay, so let's go do that. So we're going to do machine learning workshop image classifier is what I'm going to call this. So this is the first, this is like the only non-regression algorithm that I do here, but that's all right. So this data set actually comes with Scikit Learn. So you actually have to import the data sets module to get it. So I'm just gonna call all of these guys. So now we're gonna load our data set. So that's this line here. It's just dataset.load digits. Okay, that's our data set. And we're now gonna just kind of plot some of those example pictures there. So this is gonna plot kind of the first, I think, 4 digits of the data set. Here you can see 0. Okay, that's the same picture as what I had here. So that's how I got that picture. Anyway, so you can see here that, you know, it has basically pictures of the digit and a label that corresponds to the actual integer that number is. Okay, so now we want to, you know, do some more data engineering. So Here we're going to separate the labels, so that's the actual number, from the images. So just call digits.target, so that's the labels. And for the images, it's digits.images. So if I look at images, for example, dot shape, let's say, we can see that it has 1,797 images that are 8 pixels by 8 pixels. Okay, and similarly, labels dot shape, it's just going to be a list of 1,797 integers corresponding to the 1,797 images. Okay, next we're going to flatten our images. So Scikit Learn doesn't do convolutional neural networks, which is a bit more of an advanced topic, so I won't cover it here. But a convolutional neural network is essentially a neural network where you can input a picture and it does some convolutions on those pictures to do to extract features. So it'll do like edge detection or color. You know, it can actually well, edge detection, I guess, is the main thing. So Scikit Learn does not have that functionality. So in order to do image prediction using Scikit Learn, you have to flatten the images into arrays. So instead of being an 8 by 8 image, it's going to just be a 64 array of values. So we do that. And now we again split our data into testing and training data, as we always do. Perfect. We now define our neural network architecture. So, okay, hidden layer sizes. 5 by 5 by 5 is kind of bad. So let's go with 50 by 50 by 50. And here we're not, so before we were using the MLP regressor. So now we're using the MLP classifier. Everything else is the same. I'm still using Atom. I believe I don't specify the activation function. So it's going to use the default activation function that is used in this. So you can go on their website and find out what that is. Okay. It's probably a sigmoid activation function. And again, we just have to do classifier.fit. And we are training our neural network. It's trained. You can actually tell it to spit out like what I have in here. Let me just go verbose is equal to true. I'm going to put that into there. All right, so that'll actually tell us, that'll show us the actual training process. So there we go. Now you can see it. All right, so it stopped after 86 iterations of training. We're now going to predict on the test set again. And now I'm going to generate a confusion matrix. So I copied this code from another website because I've never actually generated a confusion matrix before. So don't ask me what everything does here, but I'll show you the confusion matrix. Okay. I wish I could make that bigger. That's okay. I'm going to just copy the image. I'm going to paste it into here and make it bigger. There we go. All right, so the confusion matrix basically just tells us how well our neural network did. So it takes the predictions and it says, you know, for the predictions that were 0, how many of them were actually 0 in the data set. And so you can see here that it actually, so if it's, you want everything to be on the diagonal. So you can see that our neural network did a pretty good job. And you can actually see based off of the numbers that it didn't do a good job on where the confusion lies. So for example, well, the highest confusion is 2 actually. So for example, 3 and 9 get confused by the neural network a lot, which makes sense, right? For a very pixelated 3 could look like a 9. Also a 4 and a 9, which makes a lot more sense because sometimes people draw 4s with, you know, it looks like a 9, but instead of a circle, it's a triangle. You know what I'm talking about. Anyway, that is an image classifier using Scikit-Learn. So that's all I had prepared for today. Seriously, I hope you guys found it interesting. I hope you found it easy to understand. I've never actually done a tutorial on deep learning before. I've never tried to teach anybody deep learning before, so this is my first time doing this. And I was, thank you for coming out. I'm going to stop the recording now.